Hello, everyone. Good evening. The class will begin. We'll probably start in 1 or 2 minutes. Let me start to share my slides first, and then meanwhile, let's wait for the other students. All right, class. Let's start to roll. So today, I will talk about two things. Hopefully, we have enough time to cover both. The first thing that I would like to introduce to you is assembly. So we will go through some basic like instructions or like the different kind of like different formats of instruction for x86-64, and I give you a quick walkthrough for assembly, especially for x86-64 assembly. And then the second part, if we still have time, then I will walk you through some useful reverse engineering tools that you may need for your future assignment. Okay, so first let's start with assembly. So first of all, let me just ask you, how many of you have like read or have known about x86-64 before? And just type in chat so that I know whether you heard about that or you know about that or you don't know about that. Cool. Yeah, I see. Some of you heard about that, but most of you don't know about that. That's okay. All right. Yeah, I got it. Thanks. Okay, so it seems to me that most of you not like really reading that seriously before, but I want to tell you that it's okay that you have never read the instructions before, because it's not that hard, especially like grammarly speaking, it's relatively simple. And it's gonna be simpler, easier comparing to like other languages like C or Java. It's gonna be very easy for you to understand what those instructions are and what they mean for. So I wouldn't be worried too much about not knowing them. And today, while I'm walking you through about those essentials, I'm also going to teach you how you can get to know about those like instructions. So the way that I'm going to teach you is that I'm going to give you this high level, or say like the structurized format, give you this like structurized knowledge about x86-64. And then there will be things that you don't know of, such as like the mnemonics, the meaning of those mnemonics or those registers, which is fine. So it's like, you're learning a language, and then today I'm going to give you all the grammar of the language, but still you have to know like the meaning of those words. But then it's going to be easier for you because, or say it's actually, I would say it's quite straightforward, because what you need to do is just like look in the dictionary, which is in this case, it's like the reference of x86-64. You just look into that and then get the meaning of those mnemonics. So it's, grammarly speaking, this is very easy. There's no complex structure or no like fancy data structure or like the layout, like pointers or like class objects. There's no such thing. So which is nice. So it should be pretty straightforward for you to understand and to know how to read those instructions. And then all the left that you need to do is just like have a dictionary with you, and then you can just look it up once you don't know about the specific operands or mnemonics. Okay, cool. And then also, guys, I mean, this also is important to make sure that you understand that. If you don't, please speak, because I want to make sure that you know it so that you will be able to finish your assignment. All right, so first, let's start with this instruction. Push RBP. Can any one of you, or say that, can you guys tell me, do you understand or not understand this instruction? Yeah, pushing into the stack, push into register RBP, that's correct. Some of you don't know it, that's fine. I'm gonna tell you right away. Okay. So let's start with this first. First of all, push is like a verb. So it's like you do something. And usually for instruction, it will start with a verb. And also like the way that we call it is called mnemonic. So this is mnemonic. And what it does is that it specifies an operation. Okay. And then the second part in this case is that it's RBP, which we always just like we usually call it like operand. Like it can be a register, it can be a memory. And let me know if you don't know about register. Have you guys heard about register before? Do you know what register is? Yes? Good, good, awesome. Yeah, sort of. Okay, yeah, that's fine enough. Okay, so RBP, like register, you can consider that as a variable in your CPU. So it is a variable that has been prefined before. And when I say prefined, I mean, it has a name already. You don't have to rename it. There's no way for you to rename it. So there is a name. And whenever you say this name, you are referring to this specific, like a variable. And usually those are something that you can just keep reusing throughout your instructions, throughout like x86-64 instructions. And that is called like a so-called a register. And if you look at the actual CPU or the chip, you will see like an actual, there's really like an actual specific location that just to store this specific register, such as RBP. And when I say RBP, it is a register, and it is a register with 64-bit. And later on, I will talk a little bit more about registers with different like bit and with different notations. And then let's back to this instruction, push RBP. What it said is that it's going to push the value of this register RBP, which I just explained what register is, to the stack. And I will talk about stack later. Okay, so far, but I mean, I think most of you have known about stack as a data structure, right? Let me know if you have never heard about stack before. If you don't, please let me know, because I can't explain this to you very quickly, and don't be shame about that. Okay, good. So, stack is a data structure, and actually, if you look at the computer, there is a specific part of the memory that is, I wouldn't say specific part, like this part will be changed, but like for in memory, there is stack that will in charge of storing temporary values. And what they said here is that if, for example, if the current register RBP has a value, say 1, and then it will just like push this value 1. So it's like copy pasted this value onto the bottom of the stack. So if you look at the stack, you know that when you do push, it's kind of, there is something that is like push forward, because stack is kind of first in, last out, right? So you just push this value to the stack. If you look at RBP still, the value inside RBP doesn't change. So if you look at the register, the value doesn't change. RBP will still with the value of 1. But if you look at the stack, you will find a new element with the value of 1 at the bottom of the stack. All right. Right. And then Eric says you can remove a plate from the bottom if you're quick enough. Oh, okay. Yeah. It's like plate. Yep. Good. All right. So let me continue. And as I said, register again. Register is a location that a CPU is able to visit very quickly. So it's a variable. You can just consider that as a CPU defined variable. That will be good enough. Okay. All right. And then in terms of the notations of our registers, I just talked about RBP, which is here. If you can find my mouse here, right? And then besides that, there are a whole bunch of all different kinds of registers. There are RAX, RBX, RCX, and like back to decades years ago, like when people started to define those registers, actually many of those registers, they have a specific purpose. But now people start to make it more generalized. It's just like, it's because people, or say the new design no longer requires those registers to be that specific. Like those specific registers, they can be relaxed. They don't have to be specific for a particular like part of the CPUs or part of the like memory during the execution process, so that it can be reused or it can be used for other purposes. But so far, I just want to know that those are registers. And for those registers with 64-bit, that always start with R. And then for those with like a lower 32 bits, then you just do EAX or EBX or EBP. Basically, each row here represents a same kind of like a same unit or same location. And the only difference among those 4 is that for this location, it contains 64-bit. And then the lower 8-bit, to refer that, we use like AL, BL, CL. And then for the lower 16 bits, we use AX. And actually there is another, which is between the lower 8 bits and the lower 16 bits, which is bit number 8 to, or say bit number 9, if like depending on how you start with your index, right? So it's like bit number 9 to bit number 16, that is AH, but we just don't show it in the table. And then for the lower 32 bits, it starts with E, or like for those that is shown on the right, it's like R8D. Use the letter D to notate that this is a 32-bit register. And then for the 64-bit register, that is R, always just starting with R. So you see that, and again, like I want you to know that when we say RAX already cover EAX, AX, and AL. And that is important because in some of the instructions, you will see something like you change the value of RAX And then you probably want to compare the value of AL to something. And you want to be aware that by the time that RAX is changed, AL or AX or EAX is also changed. So their value is changed along with RAX because essentially RX, EX, AX, and AL, they're referring to the same location, just like the same location with different like a partition of that location. All right, so far so good? Good. I guess that's a yes. Yes, good. Thanks, Eric. All right, then let's continue. Then let's talk about stack. So this is like the destination or say the object that push tries to operate on. And since you already know about stack, you know the data structure, you know that this is first in, last out. And memory wise, so it's like stack is in memory. So you will have address. And if you still remember, not yesterday, sorry, it's like 2 days ago, right? In our last lecture, we talk about endiness, and then we talk about like this notation of memory address. So when we do stack, when they start to push, you need to keep in your mind that when they say like push one or push RBP, it always just push that to the low address. So the stack, if you look at the right hand side, so it's like this is high address and this is low address. And whenever you push from the bottom to the top. So it's like you push onto the low address. So the like if you push more and more and more, we say that the stack will grow, right? Because there are more and more elements in the stack, and then the elements kind of grow to the bottom. It's to the down, like down's direction. And when I say down, it means like to the lower address. All right. Okay. So now I got some questions. I'm going to answer this right now. So what is the difference between RX and R8? That's a very good question. It's like you have two different variables. One variable named A, the other variable is named B. So, I mean, that's the difference. They're different variables, but like if you talk about like structure wise or register wise, what is the difference? Usually there's no difference. I mean, originally there is difference because like RX is more of the general register, whereas R8 has some other meanings. But then now they're both kind of like general register. There's no specific use unless there's some other purpose, like regarding calling convention. But I will talk about that a little bit later. It's not, I don't want to go to the rabbit hole. We don't have to know that much. But to answer your question, just on a high level, that's like not really a difference between RX and R8. So just as long as you know that they are registers, they are variables. It's kind of CPU defined variables with different names, you're good to go. All right. Okay. And so far, I guess it's good. We just talked about stack, and then now let's continue. Next instruction, move RBP RSP. Can someone tell me what this means? And if you don't know, just type no in the chat. Moving value from one register to another. Yes, that's a good guess, Samuel. That's correct. It moves RBP to RSP, or moves value from more contents to RBS. I don't know what you mean by RBS. I guess you mean RBP, right? Or RSP. Yeah, move RSP to RBP. Yep. Cool. Okay. Yeah. So you are answering this correct. Although there's one thing that I would like to talk about. Let me see. Okay. Yes, it's right here, but I will talk about that later. So first of all, move RBP RSP is actually move the value from RSP to RBP. Sorry, give me a second. I'm trying to come up, annotate this, but I don't have a pen with me right now. Just give me a second. I need to log into the Zoom using my another account. One sec. Okay, here I am. So in this specific instruction, it's the opposite. Like, because usually it's we think this like from the left to the right, but this is counterintuitive. This is from the right to the left. And I will tell you why later. Okay. So for now, I just want you to remember that whenever you see an instruction like this, especially that in this format, and I will cover, like I will talk about what I mean by format later. It's that you move from the right to the left. Okay. And again, move is another mnemonic. It's like push. And here, RBP and RSP, they're two operands. For some instructions, they have one operand. For some instructions, they have two operands. And in this case, there are two operands. Okay. Okay. And now let me talk about those like so-called syntax, format, those things. And as I said, this is a very counterintuitive because we usually just think that we should move from the left to the right. This is normal way that we read. That why you want to have this. So it turns out that they're just like two syntax when people design the expression of instructions. And if you look at the actual binary, these two are essentially the same. It's just like when people speak or say when people represent those instructions encoded using a more understandable language, which is like those like letter, operand, and mnemonics, people tend to have different like different orientation, different directions. And actually Intel is the one that uses the more frequently, like comparing to AT&T. So this is Intel and this is AT&T. And the reason for that is because of the conditional, how to say, like the conditional comparison, or so the conditional jump. Yeah, let me rephrase that. It's not really conditional comparison. There's no such thing. There's only comparison and the conditional jump. It's just like Intel has a better and more intuitive representation for conditional jump. And that is why people tend to use Intel, although that people has to suffer this part. So it's like people think that it's okay for me as long as to remember it's always from the right to the left. The destination is the first. But I care more about like making sure that I understand the conditional jump in a more intuitive way. Okay. All right. And then the reason, and then like, again, if you want to compare this to, you see like there is a difference format wise. This one for Intel, it doesn't have this percent sign. And then for AT&T, it has percent sign. It also has a more straight or more specific instruction representation because here Q means that you move 64-bit. All right. So far, so good. I guess so. I saw many of you are chatting, and then thanks for, keep commenting and then like talking with each other for this Intel and AT&T syntax. Cool. Okay, now let me continue. Yeah. Here we go. Let me clear this up. All right, and then in terms of move statement, there are more possibilities for operands. What I have just shown here is one case, which is you move from one register to another register, meaning that you copy paste the value from one register to another register, okay? But there are other possibilities. For example, for the first one, can anyone guess what that means? Yes, set RAX to 0. That's nice. And then what about the second one? And keep in mind that we are using Intel syntax right now. Okay, you may a little bit confused about the second one. So the second one, you said second one is scary. Yeah. It is scary, but it's actually not very hard to understand that. Let me walk you through about this. So RCX is a register, as you guys already know, right? And RCX will have some value stores in that specific location. And what it said here is that you want to use RCX, take that value out, and then take that value as a memory address. And you want to refer to the location with this specific address. So it's like you do star RCX, and then RDX is equal to star RCX, and putting that in a C format, in a C way. All right. So, and here we call this as like an absolute. And then here we call this kind of operand as immediate. All right. So it's like this is absolute, meaning that this is an address using RCS acts as the address value, like the absolute address. Okay. Okay. And then the third one, anyone could take a guess? No? So you have no guesses. That's very nice. Yes, offset. Kristen, you're right. So this is offset. And then to be more specific, this is like you want to move. So it's a memory, right? And then the only difference between this and then RCX, the above one, is that this address contains, it's like a base, right? And then contains an index. This is like an index. For example, if you have an integer, int a, okay, say there are 10 elements, then what you could do is you want to maybe refer to A5, okay? And then you will have RBP, maybe that is the base of A, plus 4 times RAX, or say in this case, let me do 4 here. It's going to be 4 times RAX, which is RAX, then in this case, it is 4 or 5, whatever. If I put 5 there, then it is 5. If I put 4 here, then it is 4. Just like the index. And then what does this mean, right? You may wonder, what does this mean? And this is because actually what you want to find the address of A10, sometimes it's not really using RBP, because RBP usually just refer the base address of a stack. But if you want to refer something like an argument or a variable that stores inside the current stack, it may start with RBP minus 48. So here you want to consider this RBP minus 48 as the actual A here. And then this is just a way for you to index the specific element. And then in short, this means that you want to move this address's value, the memory, which is referred by this address, and you want to move that value from the memory to the specific register, ESI. Okay, I know this is confusing, so, but is this clear to you? Base for stack, yes, this is a base for stack. And then if you come back to, stack, well, we just talked about this before, but I didn't go into the detail about the stack. So let me go there, right? So this is the stack. And as I said, like stack is usually, this is the top and this is the down. This is top and this is down. Usually we use RBP to specify the top of the stack. Okay. And then what's the difference between Q word and D word? That's a very good question. And I want you to answer, or okay. I don't want to take a guess. I think I want to save some time, but I can just, let me tell you directly. So that's a very good question. And then you can somehow observe the difference between these two. Like this register, this guy starts with R, which means that it is 64-bit, right? And then this guy starts with E, and this guy is for 32-bit. So here, the difference between Q word and the D word means that this is quarter word, so it's like 4 words, and this is double word, so this is like 2 words. Okay, so that is the difference. Q word means there are 4 words, and D word means there are 2 words. And each word is 16-bit. So double word means that this is like 32-bit pointer, because when you have this, you only have the address. You don't know, starting from this address, how many bits that you want to get from starting from this address, right? So that's why you want to have a specifier to tell them that, hey, I want to start from this address to get 16 bits, which is 2 bytes, or Q words, like 64 bits. Yeah, 64 bits, which is 8 bytes. Make sense? Sorry, I am wrong. This is 32 bits. This is not 16 bits. So this is, D word means this is 60 bits, and then like this is 4 bytes. All right. Cool. Let me continue. And I said more instructions. Now let's come with a little bit more like more complicated thing. Okay. And first of all, this is Intel syntax. Keep in mind that this is Intel syntax, because right now we don't have, I'll put a dot over here. There's no such thing. We don't have this percent sign for each register. So this is a comparison followed by a conditional jump. All right. And before that, let me just answer the just question very quick. RBP 4 times something means A for, I mean, depending on where the A is. That's why I'm talking about RBP, and then like RBP minus 48, depending on where the A is. If A is at the top of the stack, then it's RBP. But if A is in the middle of the stack, then you want to use RBP minus 48 to specify the like the array of A. Okay, so now let's come back. So in this case, first of all, the first guy, like this, sorry, the first instruction, this one is a comparison. Like CMP is short for compare. Okay, and then compare RX with RBX. And then the next is JGE. And it means that jump if it is greater or equal to something. And this two has to be kind of like work together. Actually, I mean, in the details, what it does is that in the first instruction, when I do a comparison, some flags, which is also a kind of register, which I don't show you in the table, but there are some other registers that is responsible for kind of remember the comparison results. There are some flags over there. But for you, what you need to know is just like, this is a comparison, followed by that, if we have a JGE or there are other kind of like conditional jump, or just compare these two registers coming from the comp instruction, and then it try to jump to this location if the condition is satisfied. And here, this is associated with this. Okay, so it's like GE is it's short for greater than or equal to. And this is actually the nice thing for Intel syntax, is that if you have compare followed by JGE, and you just put, it's like you put a GE right here. But if you're doing this in AT&T syntax, I don't know if I have a slide. Okay, it's right there. Okay, so I will go there. Let me clear this up. But if you go to AT&T syntax, you will see that the order is opposite, which is a little bit harder to understand. I mean, depending on if you're feel this is natural, but you have like I mean, there are people that think Intel's better because they prefer the compare statement is more natural. But then there are also some people that prefers AT&T because they think that it is okay that compare is unnatural, but the move statement, those statements is key to be natural. So anyway, so I just want to know, I want you to know that for AT&T, you see that here it's still Rx is greater or equal to RBX, but this is in the opposite order. So you need to flip the order of this two and then do this greater or equal to. All right. Question. The result of a comparison go to some registers that compare can see. Yes, exactly. So those are the flags. Like there are many flags that is associated with like compare instruction. And essentially what it does is it does a subtraction actually for these two registers. And then it sets like a 0 flag or a sign flag. And then when you do this instruction, it will check those flags value. Sorry. Okay. Question. What does XX refer to? They are bytes, but more precisely, they are a location. They're the address of the other instructions. So it means that if this is true, then jump to the instructions at a particular address. And you will see this later. You will see that in a in-class practice very soon. Yes, and as King has said, it's a label or a memory address. Exactly. Very good. Okay, so next, it's about prefix. Sometimes we have a prefix for instructions. It's like instructions no longer only have a verb or say a mnemonic, but also it will have a prefix. For example, in this case, it has this wrap before like the move statement. If we don't look at wrap now, if we only check this, you should be able to understand what it does. It's kind of, or yeah, I mean, you should be able to understand what it does. It's like you move a byte from this place to that place. Okay. But then if you have this rep prefix over there, it means that you want to repeat and to register ECX is equal to 0. And this rep specifically means that you have to look at ECX. And you see that actually this is a very interesting like thing. It's that ECX is there's like, it's not all the register. It has to be ECX. And this has been hard coded into this prefix REP. And this comes to like, back to a long time ago, every register has its meaning, has its purpose, and the ECX, one of the purposes for ECX is to handle instructions such as repeat instructions. Okay? All right. So that is pretty much what I want to talk about different kind of instructions. And I want to give you like different kind of formats, different kind of grammar for a language. And for the rest of the work, it's going to be give it to you to understand those vocabulary, understand the meaning of those words by looking them up into a dictionary. And the more you read it, then you will be more familiar with that. It's like you get to learn a foreign language. You handle them more, you deal with them more, and then you don't have to look at dictionaries every day. Then you just like memorize it in your brain because you've seen this for many times. Okay. Question, we will be coding. No, we're not going to be programming assembly language, but you will be asked to read assembly language, which you will have one practice in class. Exactly, analyzing assembly. All right. So useful resources. I want you to write this down right now because you will need it right away. You will need that in the follow-up in-class assignment, which will happen in minutes. But also, don't limit yourself to this. Basically, I just give you 2 links that has the instruction reference. It's like a dictionary that you can check, and also a cheat sheet for to quickly refer, like quickly go to understand Access 664 instructions for some specific mnemonics or operands that you don't know. Okay. Yes, and this is all to aid in reverse engineering. Okay, so far so good. Are you guys ready for a class practice? Yeah, the next one is gonna be no. Do you need more minute?
Could someone else try the cheat sheet? Because it's telling me it's forbidden for me, that I don't have access to it.
Sorry, say it again.
It's telling me I don't have access to the cheat sheet.
Hmm. That's very interesting. Can someone else try that? No. Okay, I guess they just change the permission. Damn. Okay. Then we just lose it. But if you just search Google Access 664 cheat sheet, you should be able to get some. Yep, this is unfortunate. Last time I opened it, which is last semester, it still works. Please do not do any illegal stuff to access that. You don't have to really use this one. You don't have to stick to this one. You can Google it. You will also get very good other cheat sheets, please. Okay. I'm looking at Jack's chat. Jack's asking if this is a good one. Just let me take a, yes, I think that one is good. So I am going to put this link in the slide right now. And guys, you can take a look at the Zoom chat. You will get the link from Jack, which is also a very nice cheat sheet. And 1 second, let me change my slides right now. Whoa. Thanks, Jack. This is very useful. All right, so I guess you're ready for our in-class practice. Let's start. So let's try to play this. And I will show you how to start. First of all, make sure that you have either Cygwin or like a Linux system that you can use Command NC. All right, and then I am going to show you here. You can also use Mac. Mac also has NC, so you know. So I'm gonna show you here. What you're gonna do is that you just follow that command, NC followed by the address and the port. Okay. And then you will see that it starts to ask you for your ASU write ID. And please put your ASU write ID over there, or you can put your, yeah, I mean, actually, now I think about it, you can use either your like handle, your ASU, or your like 10-digit ASU write ID. Either is fine. I can check who you are. So make sure that you type your name or your I mean your ASU write ID or your handle. And yes, this is basically assignment. This is going to be part of assignment number 5. And I don't use Docker because I need specific features from virtual machines for my research, and Docker won't support me that. Okay. So guys, Let me know if you can connect. All right, I'm gonna write that. That's my handle. Good. Everyone, yeah, many of you have connected. That's great. So you see that you have challenges now. You have 1, 2, 3, 4, 5. You have 5 challenges. And let's work on the first challenge together. Hit 1 to go to the first incomplete challenge. I'll just hit 1 because I know that I haven't started, so I don't have my first challenge answered yet. Okay, so now you see that it's assembly code for function assembly 0, and then with 3 arguments, arg1, arg2, arg3, and then it gives you a bunch of assembly, and then it asks you the value of ex and ecx if this function was called with argument 10, 73, and 89. Okay, and guys, you may notice that you got a different number for your function, like different value of the argument in the function. And I make that purposely because I don't want you to take the answer from me. Okay, so now let's start to work on this together. First of all, we know that this is a function, right? So this is a function with 3 arguments. And then the first question that you need to know is the so-called calling convention. I will write it here. By the way, guys, I'm looking at you chat, and thanks for helping each other to figure out how to connect, especially if you're using PuTTY or using Windows. Thank you very much. Okay, so I'm gonna write here, this is so-called calling convention. What does it mean? It means that there is a hard-coded specific kind of rule, that's why we call it convention, that people keep using it in assembly, in your, like, say, ARM or x86 or x86 64. And here for x86 64, the calling convention is that for a function, those arguments, they're specific to the specific register. So the first argument will always just go to RDI or say EDI, depending on the architecture. If you're using x86, oh no, actually let me rephrase that. It's actually not quite true. So for x86 64, it will always just use RDI. And then let me remove that. I don't want to confuse you. And then for the second argument, it will always referred by RSI. And the third will be RDX. And there are actually more. For what about the fourth one? What about the fifth one? What about the 10th one? Right? So, but you can get this information if you just search online. You will get, just search like calling convention x86 64. You will be able to get that. And now let me see if I can have a. I'm trying to see if the cheat sheet has that or another web page has it. Just give me a second. Yeah, this one gives us this. So if you search, you can get this web page very quickly. Yeah, and by the way, Kinhan, thanks for you to copy paste this. Yeah, so you call a function, the first integer or the parameters, like the pointers, they will go to RDI, RSA, RDX, RCX, R8, and R9. And this is for x64, which is different from x86. All right. Thanks. Thanks, Sam, for sharing this link of this of my screen. That's nice. Cool. Okay. So now let's just come back. Let's continue. All right, let me make it big. Okay, so now we know that arg1 goes to RDI. And then we know that EDI is the lower bit, right? So it's the lower 32-bit for RDI. And in my case, here we have 10, 73, and 89, these three arguments, so that we know that EDI is equal to the value of 10, right? And then ESI is equal to the value of 73, and EDX is equal to 89. So far, so good? Cool. All right, now I'm going to continue. So for the first statement, can someone tell me what will happen after this move statement? So the move statement moves which value to which value, which register to which register. Yes, exactly. EX will be equal to 10. So EX will be equal to 10. I'm going to write here. Cool. And then what about the next? What will happen? Nice. ECX is going to be equal to 73. And then pay attention to this. Compare EX, EDX, and then JGE 9BF. So tell me if it's going to be jump to there or not jump to there. Yes, it ignores the jump, because here when you compare EAX with EDX, which in this case is, let me put here again, is 89. We know that EAX is not greater or equal to EDX. So we just keep where we are and continue the execution. Okay, so jump is ignored, and then continue. We have this add statement. So what add does is that EAX is the destination. It's the destination operand. So it will do EAX plus EDX and then store that to EAX. Okay, so that in this case, can someone tell me what will happen after this instruction? Exactly, EX will be equal to 99. Very good. And then the next one is a stop. Again, similar to add, the operation, after the operation, the value will be stored in the destination operand, which is the left operand. So we have ECX is equal to, what is the value? Yes, minus 16. I will put minus 16 here. So ECX is equal to ECX subtracted by EDX. So that is minus 16. But remember that if you look at the register, it's just memory, right? So it's just memory that doesn't really have a sign over there. We'll say if you want to put a minus number over there, then what will the register looks like? The register itself doesn't contain a sign, right? It's only that you have a C or you have a higher level language that specify that, oh, look at this memory. And this memory is actually a negative number. You want to parse that. You want to interpret that by looking at the memory. So then how you're gonna convert this to an actual like a value stored in the memory in register ECX. I'm gonna pause here because I saw some of the questions. So shouldn't the add step be 83? Since it's ECX, I am okay, so I guess what you guys talking about is the add instruction, right? So Marcus and Slice and Tough, feel free to chime in.
Yeah, the add that you did EAX equals EAX plus EDX, and the add
Oh,
says E.
yes.
That's why we were all saying it's 83, not 99.
Yes, that's a very good catch. Thank you. Yes, that's a typo. So EAX is equal to EX plus ECX. So in this case, it should be 83. You're right. Thank you very much. Cool. Okay, so now, again, let me see. Okay, nothing changed based on that, right? Yeah, it's only EX gonna change. Good. And then the next is the sub, right? And then I said ECX is a minus value. And the way that works is that you want to check the value of E, like the maximum possible value, which is, again, this is like 32-bit. 32-bit, right? So that means that the maximum value would be F, 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 F. It's like 8F, right? And that is actually -1. So in your register, if you stored a negative value, what you want to do is that you want to kind of like have this -16 and then +1. All right. And then can someone just use your calculator or Python to calculate this and give me the value? And I am also going to calculate this on my end. Question, wouldn't it be 4F? So 1F is, yes, this is 32 bits. And let me calculate this again. So 1F is 4-bit, right? Yeah. So and then for 32-bit, then you need to have 8 Fs. That's correct, right? So that's why we need 8 Fs over there. So it's like 2 Fs represent 1 byte, which is 8 bits, right? Okay, I guess you got it. So then this is the value that we get. Cool. And now we have this, and then let me X this. Let me copy paste this value just in case that I want to store this somewhere. And because I need to exit this window so that my annotation will be aligned with our display. Okay, so now we get the value of ECX is actually this value. It's pretty huge. So let me remove this and then actually just erase this. Hopefully my eraser is precise enough. Okay, that's nice. So it's gonna be 429, 496, 7280. All right. Okay. And then this instruction, the jump, it says just jump to the end and there's nothing, just returns. Cool. Now we have all the values that we want for the registers. And what it's asking is what is the value for EAX and ECX, right? I will go over it again, how I change the value, how I change the negative value. And then right now, let me just finish this. Hopefully we're calculating everything correct. I'm also starting to be nervous, but if I don't, it's actually nice that we just need to recalculate the negative things again. So 429, 496. Okay, and then ask for EAX and ECX, right? So EX equal to 83. Okay, cool, I got it. So I'm correct. I solved the first challenge. And you will be asked to solve the other 1, 2, 3, 4 challenges later on. Like if you like finish this one with me together, but if not, of course you need to solve this one as well. And this is going to be your assignment. Don't be hasty. It will be released sometime, I don't know, like sometimes when the all assignment will be released. So right now, just like during this class, you have the time to finish the first one. And if you don't, that's also fine since you already have the solution from the video. And then for the rest of the assignment, like the other challenges, it will be released again after all assignment will be released. But like after this class, I'm gonna probably turn it off for the server, just so you know. Okay, and now let's go over this calculation of negative number again. Okay, so let me clear this up, and then let's have another video. I think that will be more cleaner. Suppose that we want to calculate the value for hex 16, right? And then we know that hex 16 is stored in register, say ECX. Okay, so the first thing that we want to do is that right here. What is the maximum value of ECX? Okay, to answer that, we know ECX is 32-bit. So it is ECX is is 4 bytes, right? And then you know the maximum is hex 8 F's together. Okay, so this is step number 1. And then step number 2 is that once you get this maximum number, yes, those are all F's. Sorry that I have a very terrible handwriting. So after that, we want to use this maximum. I'll just call this max so that I don't have to write terrible 8 F's again. Max plus 1, and then minus 16. You can change this to whatever numbers. If this is a minus, like minus B, then you want to change this to minus B. Okay? So that in this case, you will have this number plus 1 minus 16, and you will get your answer. Question, is plus 1 to account for the negative sign? Yes, although this is not really the way that register represents, it's just the way that we calculate it. Okay, so this is just a way for you to know how to calculate the corresponding and signed value for negative number. But this doesn't mean that it's the way that like the computer is designed to represent the or say the computer is designed architecture-wise, or say the hardware-wise that they calculate in order to get the number. Okay. All right. So no more questions? I guess that's yes. So how do we do that with Python? The calculation? Yeah, it's pretty easy. You know that the maximum, right? The maximum is for ECX is going to be x. So just put 8 over there. And then plus 1 and then minus 16. That's it. Very easy. Cool. Or you could do is like as King has said, if you just convert it to unsigned binary, you can also do that. All right. If things are okay, then let me just like exit this and then let's go back to the slides. Okay, so next, then let's just quickly go over some of the content for reverse engineering tools. There was supposed to be another demos, but too bad that we're running out of time. So let's just go through those tools today so that you will know what kind of tools that you will probably need for your future assignment. And actually, it's kind of nice so that you can spend a weekend to figure it out, to install that in your local or in your Linux computer or virtual machine in whichever way you like. Okay, so then the first one, the first thing that I want to say is that like there are so many different kind of reverse engineering tools. It's just like you go shopping. There are like games, different kinds of games. There are like electronics in different brands. There are clothes in different brands. So it's most of like you want to pick what is the best to you, what fits the best to you. I may think that tool A is fantastic, but actually you may think that tool A sucks so much. And you may prefer tool B, but I don't like it, which is fine. Just like people will have different preference. And right now, what I'm gonna show you is just tools that I normally use or say I think that is usable, that is useful also. But also feel free to explore other tools. And actually, like for those very great hackers, actually it's quite of interesting that you will realize that they do have a strong preference of what tools that they like. And it's like, you are a warrior and you want to select the best sword, you want to select the best arm that fit the best to you. So it's just gonna up to you guys to decide which one you want to like use. And assignment wise, we're not gonna we're gonna specify or say like force you to use any of the tools. We're just like give you the challenge and then you can decide what tools to use in order to solve those challenges. All right. So first of all, static tools. So those tools that are, when I say static, it means that you don't really run the program. You don't really execute the program. But then instead, what you do is you just kind of eyeball it. Use the visualization that is showing through the tool. Okay, so for example, the one is called realf. We have used that previously in our previous lecture. And the Opsum is another tool that can help you to get the assembly of a program. And let me show you real quick for Opsum. So for Opstomp, let me see. Okay, there is an example right here, which is nice. So let me do obj dump dash d. D means to disassemble. Okay, and then give it a path of the binary. And I'm gonna use less commands so that it will not like go all of them right away. So we can see this line by line. So you see that those are the instructions. They will give you both the byte and the associated instruction. And those instructions like what we have for today. It's just like this one, you know that this is like in AT&T format. You can also change the format. If I do opt dump help, hopefully this is not too much. There is a syntax argument that you can change. Let me see, can I find that? Okay, here. Display the instruction in the AT&T and then that syntax. But I need to have more. Okay, so it's dash M, dash capitalized M. So you can change that. You can change your syntax to whatever you like using this dash M switch. All right. Okay, so this is for opt dump. And then you may want to read the bytes. It's like what I did last time, you know, when I used Vim and used this like XSD command. But what you also can do is use hex dump. Okay, so hex dump like a file. Let me see if this works. Yeah, it should work. A example. Right, so you got those value, and the leftmost is the offset. This in this way. So see, like this is the offset. This is like starting from offset 0. Those are the 1, 2, 3, 4. Like those are the first 16 bytes. And then this is like the, you know, row like offset from 1, 0, hex 1, 0. And this is another 16 bytes, right? So you can read the bytes using hex dump. All right. Although like opt dump, it gives you this nice disassembly, but sometimes it could be imprecise. Although for most of the cases, or say for those assignments that you're going to be given, they're mostly correct. I don't want to challenge the correctness of opt dump, but I just want to know that in some cases, it is possible that opt dump is giving you a wrong answer. Okay. And the next is dynamic tools. GDB is a tool that we use a lot, but GDB is kind of, I mean, prime, or say kind of not too advanced, because the visualization is not very like super friendly. It's not like very good. And then so instead, what you could do is you can use GDB with plugins. You could choose either Pada or Jeff or Pound the Back. So what I use here is Pound the Back, but you can just choose between, like choose the one that you like. And if you installed the plugin correctly, then all you need to do is just like type GDB, and then it will automatically call Pada or Jeff or Pound the Back, and then you will get this specific like command or the interfaces. Usually the reason why we have this is because this is more colorful and it will give you more information. And also, if you remember last time when I do VM map, it gives you more like legend-wise information. Let me see, try this, say example, the out, right? And let's do run. So first of all, like those nice layouts, like disassemble, stack, backtrace, those visualizations, they all coming from Pound the Back. And also like the color scheme also coming from Pound the Back. The map, those color also come from Pound the Back. This is the reason why I like to use a plugin for GDB. For GDB, I mean, the features there, they're powerful. It's just the visualization needs to be improved through those plugins. Okay. And then the next is hybrid tools. Like those tools, they have more advanced features, such as the control flow graph or the decompiler features. I know that some of you have heard about Ghidra before. Some of you have tried to use Ghidra before. So like Ghidra has this nice decompiler view, which will kind of help you to reverse from this 1010 bytes of the binary to a source code. And in the next lecture, I will show you Ghidra. Like I will also show you how you could use Ghidra. It's definitely not a comprehensive Ghidra instruction or tutorial, but just like giving you a small tip, giving you a small example that demonstrates you how you could possibly use Ghidra to analyze a binary. Okay, and there are also other kinds of tools, either Pro, Hopper, Ghidra, Binary Ninja. There are many of them, and then you can just choose whatever you like. I would say that Ghidra will be sufficient for our class, and also it's free. It also has this nice decompiler version, although like other tools, they also have their strength. Ghidra also has these weaknesses. So I'm gonna leave you to decide which one you wanna use. But for me, in this class, I'm gonna show you how to use Ghidra a little bit. Okay. And then besides those tools, then, it's technique. So it's like those tools, they implement some of the techniques, right? For example, one of the example for reverse engineering techniques is disassemble. Basically, if you look at, like as we showed before here, if you have opstomp -d example.out, you see that it converts those bytes into those instructions. Actually, don't look at PLT. That's not the right. It's okay. Yeah, we can take a look at PLT's code section. But like for those, it converts bytes to instructions. And they're doing this, like this is so-called disassemble. Basically, you want to recover from a binary 0 and 0 ones or those bytes into those higher level instructions. And this is so-called disassemble. And then there are different ways that you can disassemble a binary. You can use linear sweep or recursive traversal. Usually recursive traversal is more precise, more powerful. And if you're interested in this, you can take a look at this paper that talks about different kinds of assembler and disassemble techniques. And also another thing is like function recovery. So there are sometimes that the function doesn't give you a name. It's called stripped because people want to save space. And then you want to kind of recover those back, find those function back. And that is called function recovery. And that is another reverse engineering techniques. Due to the time, I'm not going to go into the detail. But overall, I just want to know that in general, actually automatic reverse engineering can be pretty hard, and let's do open research. I will also say that like those tools, they're sufficient for us to our assignment, but I want you to keep in mind that those tools are not perfect. It's possible that the tools are giving you the incorrect answer because having an absolutely correct answer is still open research. Okay, so this is gonna be our next time's stuff and a quick trailer. You have this example, you have this binary, it's already downloadable. And then I'm gonna show you how to get the quote unquote key, the flag from a binary using 4 different kinds of ways. And then for different ways, I'm gonna use different kinds of tools. All right. Cool. And then questions I saw here. If we do not finish assemble 0, can we do this after class? Yes, you can do this. And it will be in your assignment as well, so you don't have to push yourself too hard. You can wait until the official assignment was released. And then will we be provided with resources for assignment? What do you mean by resources? You mean source code or you mean something else? Like cheat sheet? No, because you already have the cheat sheet. It's in the slides. Okay. And more question with the assignment 0 already? Yes, that counts for the assignment. That counts for the assignment as long as you put your ASU right ID property so that we can trace back to who you are. Okay. All right. That's pretty much of everything. Let me stop recording and then stop sharing.